So, today we will hopefully be showing the analytic continuation of the Riemann Zeta function. So we begin by defining the zeta function, which is the infinite sum, as written here. Zeta of s is this sum from 1 to infinity over the natural numbers of 1 over n to the power of s, where n is our iterative term and the sum and s is our functional input. So to begin the continuation, we first define the gamma function, which I'm sure you are aware of, and we define that as this integral from 0 to infinity of t to the z minus 1 e to the minus t dt. With z being the input of our function here. Now we're going to say that t is equal to pi n squared x, where n is greater than or equal to 1, and we can say that dt with respect to x is equal to pi n squared dx. Is just equal to pi n squared, and so dt is equal to pi n squared dx. And now we can sub this in. So if we sub this into gamma of s over 2, it's integral from 0 to infinity of t to the s over 2 minus 1, that's an s over 2 minus 1, e to the minus t dt, and that is equal to this integral from 0 to infinity of pi n squared x, s over 2 minus 1, x, and then e minus pi n squared x d pi n squared x, which is further 0 to infinity of pi n squared to the s over 2 minus 1 x to the s over 2 minus 1 e to the, I should say minus 1, e to the minus pi n squared x pi n squared dx, as you can see we got from up there. Now pulling stuff out of here, we get that that's equal to pi n squared to the s over 2 minus 1 times pi n squared integral 0 to infinity of x to the s over 2 minus 1 e to the minus pi n squared x dx. And we can finally, obviously that's just going to pop the 1 back on, so we end up with this final expression of pi to the power of s over 2 n to the s integral from 0 to infinity of x to the s over 2 minus 1 e to the minus pi n squared x dx. And that is our new gamma function of s over 2. Now, this is where it starts to get a bit ugly. If we divide both sides here by pi s over 2, pi to the s over 2 gamma s over 2, so then we're saying that pi to the s over 2 gamma of s over 2, and pop our gamma of s over 2 back on top, is equal to this horrible thing, pi to the s over 2 n to the s over pi to the s over 2, gamma s over 2 integral from 0 to infinity of x to the s over 2 minus 1 e to the minus pi n squared x dx. That monstrosity. Now, if we do some algebraic manipulation, you can see that 1 over n squared, 1 over n to the s even, times, that's a times, 1 over pi to the s over 2 is equal to 1 over the gamma function s over 2, integral 0 to infinity of x to the s over 2 minus 1 e to the minus pi n squared x dx. No, give me my x. Yeah, there we go. And so 1 over n to the s is equal to pi to the s over 2 over gamma of s over 2. The integral from, oh, that was a pretty integral sign. It's from 0 to, oh, ruined it with the bad infinity. There we go. X to the s over 2 minus 1 e to the minus pi n squared x dx. So now we can, or hopefully it can be seen how this is going to fit back into our original definition here of the zeta function. Hence, we can say that if I can draw a zeta correctly, first try I'll be impressed. Oh, that was okay. Zeta of s is equal to this, the sum of that, basically. Let me draw it a bit smaller. Okay, so now this is the complete form of the zeta function defined via the gamma function, and we can actually swap around. I won't. If you don't believe me on this, then I don't know. Maybe I can do a separate video explaining why this is possible. But because technically these are both sums, you can just swap them around and it works. So pi to the s over 2 over gamma of s over 2 times integral from 0 to infinity. This is equal to the above expression. X to the s over 2 minus 1 of this sum from 0 from n equals 1 to infinity of e to the minus pi n squared x dx. Oh, it doesn't like me. Microsoft to the scorn of civilization. Just to make it a bit easier to read, we're going to say that this function, little w, not big W, is the sum from n equals 1 to infinity of e to the minus pi n squared x. And so zeta of s is equal to pi to the s over 2 over gamma of s over 2 integral from 0 to infinity of x to the s over 2 minus 1 w of x dx. And this is for real s greater than 1, because we still haven't continued this, so to speak. So now we can bring into play this Jacobian theta identity, which is really useful here, and we can define, I'll leave this on the screen, we can define theta of x as 1 plus 2 times the sum from n equals 1 to infinity of e to the minus pi n squared x, which of course is just 1 plus 2 w of x, which is really nice, because now we've defined our w function, we can just simplify that. Yeah, that's all great. The other, well, now we can actually define the w function in terms of the theta function. which is great. So if we rearrange, we can say that 2w of x is equal to theta of x minus 1, and w of x is equal to half theta of x minus half. You can factor it out, doesn't really matter. Now, the theta function has a second definition, and that is that theta of x is equal to 1 over root x theta of 1 over x. Okay, that's correct. So here we can say that w of x is equal to lots of fractions here. 1 over root x theta of 1 over x minus a half, which is a half times 1 over root x times, oh, no, why did it write that? There we go. 1 over root x times 1 plus 2w of 1 over x. So many brackets, I missed one, there's one there. Minus half. Which is 1 over 2 root x plus 1 over root x w 1 over x minus half. There, that looks correct. I mean, we'll see if it's not correct if I don't end up with the correct continuation. Anyway, now we're going to pop back to our integral from earlier. Well, is it this one here, and if we sort of, what we can do is split it into two integrals, and we can say we can take it from 0 to 1 and 1 to infinity. So if we evaluate it from 0 to 1 first, that would be x to the s over 2 minus 1 w of x dx. And what is this equal to? This is equal to the integral from 0 to 1 of x to the s over 2 minus 1 of that big function up there. So 1 over 2 root x minus a half plus 1 over root x w 1 over x dx. Then I'm not going to write it all out because it's time consuming, but you can do lots of algebra here, and then you can split it further into three integrals because you end up with some sort of polynomial where one of the coefficients is w of 1 over x, and that's the only integral that you can't reevaluate. And so by the end of it, you're left with 1 over s minus 1 minus 1 over s plus integral from 0 to 1 of x to the s minus 3 over 2. That is an s, I promise. W of 1 over x, and that's the coefficient that I was talking about. Now, to do our best to sort of evaluate this, we'll take a variable y and let that equal to 1 over x. So dx is just minus 1 over y squared dy. And for our bounds, when x is 0 here, then y is going to be infinity, and when x is 1, y is 1. So we end up with the above integral becomes equal to this new one from 1 to infinity. We can say of y to the minus s minus 3 over 2 wy times that minus 1 over y squared dy term, and that doesn't evaluate to anything, or evaluates to anything, depends what you want to take the word evaluate to mean, minus s over 2 minus a half w of y dy. No, don't draw weird things. So we end up with this integral from 0 to 1 of x to the s over 2 minus 1 times w of x dx is equal to 1 over s bracket s minus 1 plus that integral at the end, 1 infinity x to the minus s plus 1 over 2, and now this comes from substituting x back into our equation for y, plus x to the s over 2 minus 1 times w of x dx. And further, you could say that, or rather, this doesn't come from that. Sorry. What we get from this is that this decays to 0 essentially, because of how we define the wy. So the rest of that integral is just 1 over s to the s minus 1. There we go, that makes a lot more sense in my brain. And then we have this, which was the integral, that should be from 1 to infinity, not from 1 to 0. Oh, that is an infinity, I can't properly draw. Go away. There we go, that's better. And so we can say that our previous, well, the total integral that we had earlier is equal to this. Now, what we can say here, we can say a couple of things. Well, if we look at this as x tends to, well, if we look at our w function, what's going to happen as x tends to infinity, all of these terms are 1 over x, so it's going to tend to 0, essentially. Or rather, we could say that it decays exponentially. I don't want to pin it to any single value. And further down here, we can see that now this is a bit of complex analysis. Yeah, sure. We can see that the right-hand side, which is this whole expression here, is invariant under, if we transformed it to say that s is equal to 1 minus s, then it would be invariant. So it's an analytic function of s, and it's defined for the entire complex plane with, it has simple poles at 0 and 1, but that's not so relevant. Now what we're going to do is skip ahead a bit, and we're going to take some function z, which I definitely can't draw right. It's like that of s. I'm supposed to be able to write Greek. Is pi of minus s over 2, gamma of s over 2, and zeta of s. Now, this is some completed analytic continuation of the zeta function. And from the above integral formulation that we have, we need to again prove that the z function, did I say eta before? I meant z. I don't know why it's z of s is equal to z of 1 minus s, because that's our proof for the function being analytic. And so what we can say is that using the property of the gamma function, pi to the minus s over 2 times gamma of s over 2 times zeta of s, that was the worst zeta I've ever seen, it looked like Pac-Man, is equal to pi to the minus 1 minus s over 2 gamma of 1 minus s over 2, and then zeta of 1 minus s. And now we're really close. We're really close to the end. There's two formulas that are used here called the I don't know any French. I'm gonna say it wrong, but I think it's legendary duplication formula. No, I'm sure there's I'll edit it in. I'm sure there's a way of pronouncing it. But his duplication formula and the Euler reflection formula, which are both complex formulas, and I'm not going to go into them, but what we can say via those two is that for the gamma function of 1 minus s times the gamma function of s, we should end up with this, or rather yeah, this is for this specific analytic function. We should end up with this pi over sine pi s. So from that we can say that 1 over gamma of s, so that's just moving that to the other side and reciprocal, is equal to gamma 1 minus s sine pi s all over pi, which is nice and not pretty. Don't forget double angle formula, that basic thing. Sine pi s is equal to 2 sine pi s over 2 cos pi s over 2. Very, very vital here. So we sub that back in, and we get that gamma of 1 over s over 2, 1 minus s, 1 over s over 2, 1 minus s over 2, over gamma of s over 2 is equal to pi to the minus 1 over... I fear that should be 1 over s. No, pi minus a half, yeah. 2 to the 1 minus s. Oh, I'm not going to have enough space. Gamma of 1 minus s cos pi s over 2. Imagine that that's there. Anyway, now we have that, we can say that the gamma zeta function of s is equal to pi to the s minus a half times, that's a great big block, pi of minus a half, that thing from up there, 2 to 1 minus s, gamma of 1 minus s cos pi s over 2 times zeta, oh that was so bad, no, there we go, of 1 minus s, which in turn is equal to pi to the s minus 1, 2 to the s minus 1, gamma of 1 minus s cos pi s over 2 z of 1 minus s, zeta of 1 minus s. And we know that cos pi over 2 is cos pi s, don't forget the s, is equal to sine pi times 1 minus s over 2 via the trig identities for sine and cos. Cos alpha is equal to sine to pi over 2 minus alpha, because they're phase shifted. Anyway, we know that because that's true, our final zeta function, because now we're going back on our substitution from earlier, where we said that the function for 1 minus s is the same as the function for s, we can finally say, and I don't think I'm going to have enough space to write this, so I'll try my best to do it quite small. And so in conclusion, we can say that our analytic continuation of the Riemann Zeta function, zeta of s, is 2 to the s, pi to the s minus 1, sine of pi s over 2, gamma of 1 minus s, zeta of 1 minus s, and this is valid for all complex values of s. Thank you very much for watching.